Hello and welcome back to non-IITN. So now we are gonna delve deep into problem solving, and we have prepared three particular lectures on problem solving, where the problems are taken primarily from IIT JAM, CSIR NET, and TIFR PYQs. Our goal is to make you understand how to think about a problem and how to approach a problem, rather than just helping you memorize tricks and solutions to typical problems. So we will go slowly through each of the problems, and we'll go through them in a way that you are able to understand that how do someone typically thinks about a problem before solving it. So we are going to try and solve about 10 problems in this particular lecture, but probably we'll do till 5, at least till you know I have planned. Nevertheless, let's start. So let us see the first particular problem. So let G be a finite abelian group of order 10. Let x dot be an element of order 2 in G. If capital X is the collection of all the elements such that x cubed equal to x naught, then which of the following statements is true? X has exactly one element, x has exactly two element, three elements, and x is an empty set. So let's see the solution. Okay, just wait a second. So let's see the solution. So x is given to be the collection of all the elements in G such that x cubed is equal to x naught, and x naught has order 2. Okay, now firstly observe that G is a finite abelian group of order 10. What does that mean? That means G is isomorphic to Z2 cross Z10, right? Is it clear? And the right, so that means that G is basically cyclic. Okay, now how do we typically try and think about this problem? Observe that, see, if x cubed is equal to x naught, what does that mean? That means x cubed whole squared would be equal to x naught squared, which will be equal to 1. So that means that the order of x, this divides 6, right? Also, x is an element of G and the order of G is 10. What does that imply? That implies that order of x is equal to 2, because, or nevertheless, so at least we get the order of x divides 10, but that means that order of x divides the GCD of 6 and 10, which is equal to 2. So therefore order of x divides 2, which means that either x is equal to 1, so order of x is equal to 1 if and only if x is equal to identity, or the order of x is equal to 2. Now if x equal to 1, if x is equal to 1, that would imply x naught is equal to 1, which would imply that the order of x naught is equal to 1, which is not equal to 2. So that's a contradiction. So therefore order of x has exactly be equal to 2. Now since it's a cyclic group, so therefore number of elements of order 2 is exactly equal to phi of 2, which is equal to 1. What does that mean? That means that x has to be exactly equal to x naught, and you can immediately verify that this would actually imply that x cubed is equal to x naught cubed, which is equal to x naught squared times x naught, but x naught squared is identity, so it's just x naught, so it satisfies it. So therefore we got only one element, so option A should be a correct answer. Let us move on to the next problem. So the next problem says that capital X is equal to collection of all elements in the symmetric group on 4 objects such that x cubed is equal to identity, and y is the collection of all those elements in the symmetric group of 4 objects such that x squared is not equal to identity. If m and n denotes the element of x and y respectively, then which of the following is true? M is even and n is odd. Okay, so they have asked about the parity of m and n. So let's see the solution. So m is the cardinality of x and n is the cardinality of y. So now observe that basically if x is an element of S4 such that x cubed is equal to identity, what does that mean? That means that the order of x is either 1 or 3, right? Now how do you get a cyclic decomposition such that the LCM becomes 3 and it adds up to 4? So possible cycle decomposition should be, so either you have all ones which will admit the identity element, or the only possibility is 3 and 1, right? So therefore x is either identity or 3 cycles. And what are the number of elements such that it admits this sort of a cycle decomposition? So therefore cardinality of x should be 1 plus 1 accounts for the identity element, and the other part you have 4 factorial divided by 3 to the power 1 times 1 factorial, which is nothing but 8, right? So sorry, I mean 1 plus 8, which is 9. So what do you get from here? So therefore this is odd, right? So therefore m has to be odd, so this cancels out and this cancels out. Now about even, so x squared is not equal to identity. What if x squared is equal to identity? So first let us analyze that. See, if x squared is equal to identity, that would mean that again order of x is either 1 or 2. But then again this accounts for the identity element, and what are the possible cycle decomposition so that you get the order to be 2? So either you can have 1 1 and 2, or you can have 2 and 2, right? So these are the only possibilities. What are the number of elements which account for this cycle decomposition, which is 4 factorial upon 1 square into 2 to the power 1 into 2 factorial. So this is 4 factorial upon 4, which is 6, and this accounts for 4 factorial over 2 square into 2 factorial, which is 3. So therefore total you get 1 for the identity plus 6 plus 3, which is 10. Therefore n is even, right? So therefore you get n to be even. Am I doing some? Okay, so we accounted for, oh sorry, so we accounted for all the elements which has order 2, or which are not in y. So therefore y so therefore y must be cardinality of S4 minus 10, which is 14. So this is even. Extremely sorry. Nevertheless, we still got the answer, but that was a wrong approach, as we just saw. So n has to be even and m has to be odd. So option B should be correct answer. Let us move on to the next problem. So what is he asking here? So let R upon Z denote the quotient group where Z is considered as subgroup of the additive group of real numbers. Fine. Let M denote the number of injective group homomorphisms from Z3 to R mod Z. Okay. And N denote the number of group homomorphisms from R mod Z to Z3. Then which of the following statements is true? See, so solution, first thing which you can probably try and observe, not quite immediately, but if you have already seen, see, R mod Z is actually isomorphic to the unit circle as a group under multiplication. As a group under multiplication. So this is kind of an observation. So what you can do is that you can take an map from R to S1, and you can just take phi of t to be e to the power 2 pi it, and then the kernel of phi will exactly come out to be z. And in fact this is a surjective map because every element in on the boundary of the unit circle will on the unit circle will account a form like this by the polar coordinate, and hence you will get a real number which gets mapped to it. So that's quite an quite an easy observation, to be precise. So it's actually isomorphic to the unit circle, and actually it's called a lattice group. I shouldn't say this exactly to be the lattice group, because Z as a group is actually what we call the lattice group. So this is the quotient of the reals under the lattice group. Nevertheless, first thing which we need to understand is that so we are asked the number of homomorphisms from Z3 to R mod Z such that it's injective. So therefore I need to identify how many possible subgroups are there in R mod Z of which are cyclic and has order 3. So this accounts for number of subgroups in R3 R mod Z of order 3, which will automatically be cyclic. In fact, what we require is that number of elements would be rather useful. Okay, now what are the number of elements in R mod Z? So basically we want number of elements in the unit circle that would typically come out to be phi of 3, because actually the number of elements of order 3 would actually be so it comes out to be phi of 3. So these are the number of elements of order 3 in S1 unit circle identified inside the complex group. So the number of elements will be the number of homomorphisms, because you can take the generator here and you can map it to the order 3 elements here. So M has to be 2, so therefore these two cancels out. A number of homomorphisms from R mod Z to R mod Z to Z3. Okay, kind of what should I be applying here? Okay, we can apply a very interesting fact here. See, R mod Z is a divisible group because it's the quotient of a divisible group. So it's a divisible group, while this is a finite group, and I had probably given this an exercise that finite groups are not divisible. Moreover, homomorphic image of a divisible group has to be divisible. So, and any homomorphic image of R mod Z will be inside a finite group, so it will again be finite, so it cannot be divisible. Therefore, the only homomorphism possible here is the trivial homomorphism, and hence N has to be 1. So option A should be correct answer. Okay, let us move on to the next problem. So whenever you are asked to find out homomorphisms and isomorphisms, these are the things which you need to keep in your mind: being torsion elements, being torsion free, being purely torsion, being divisible, having elements, having a certain number of elements of some particular order, existence of some particular element of some particular order, things like that. So for n in this, consider the set Un as a group under. Okay, so this is a very interesting result by Gauss. I have already explained it. So Un is cyclic if and only if n is equal to 1, 2, 4, p to the power k, or 2 times p to the power k, where p is an odd prime. So you just need to identify which of these are under that condition. So 5 will do. So 12 is not of any of these forms, and 9 is 3 squared. So B and D will do, right? U5 and U9 will be cyclic groups, and these won't be cyclic groups. Now see, this is such an easy problem, and it was asked in IIT JAM 2025, right? There was nothing complicated here, a very simple result and a very simple set of conclusions. Let us move on to the next problem. So let sigma be a permutation in S4 defined by sigma 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 goes to 4 exactly. The number of elements in the set which fixes sigma. Okay, that's quite an interesting bit of problem. So solution. Firstly, observe that what is sigma basically. So sigma basically represents this cycle. So 1 goes to 2, 2 goes to 3, 3 goes back to 1. Now any conjugation will preserve this. So tau sigma tau inverse will be of the form sigma of 1, sigma of 2, and sigma of 3. Okay, so this will be am I doing it correctly? No, sorry. it will be tau of 1, tau of 2, tau of 3. Okay, so it will preserve the length, right? It will preserve the length. So basically what we can see from here is that if I consider the action of S4, so this is basically what I'm trying to say is the following. So S4 such that tau sigma tau inverse is equal to sigma. So this is basically the stabilizer of sigma via the conjugacy action, isn't it? Isn't it just the stabilizer of sigma? Right. So now order of S4 is 24. So what if we are able to get the orbit of sigma, and then we can divide it by the orbit stabilizer theorem, right? So I'm just at this point I'm just guessing out what should be the answer, so I'm trying out this, right? So this implies that S4, so I'm writing S4 as G. Okay, so G sigma, the order of G sigma should be the order of G divided by the order of the orbit of sigma. And what is the orbit of sigma? And the so the orbit of sigma is basically the conjugacy class, right? So it's the conjugacy class of sigma, and the conjugacy class of sigma will just be the number of elements which preserve the same length. So these are all the possible 3 cycles, right? So this should be 4 factorial upon, so the cardinality of this should be 4 factorial upon 3 to the power 1 into 1, which is what should it be? 8. It should be 8, right? Because we had proved this in the in one of the previous lectures, that the cardinality of the conjugacy class of an element is exactly equal to the number of, which is exactly equal to the number of conjugates, and this comes out to be the number of permutations of the same cycle type. It wasn't exactly the count of the permutations, but numerically they came out to be the same. Nevertheless, so therefore the conjugacy, the stabilizer of sigma, which is whose cardinality is being asked by the orbit stabilizer theorem, this should be the cardinality of G over cardinality of the orbit of sigma, which is 24 upon 8, should be 3. So your answer should be 3. See, now I'm telling you something which you need to keep in mind. See, this problem has a very rigorous solution. Wherever you will see, if you ever come across a solution to this particular problem, you will see that there is a very rigorous solution to this problem, where they have typically tried to identify what are the possibilities for tau so that this happens. But once you try and observe this particular problem through the notion of group actions, you see it's a 4-line problem. In fact, if you are in an exam, so it's basically a memory problem. You can just calculate it throughout in your mind. And all of these concepts are already told in the lectures. So that is why it's very important for you to go through the lectures one by one and understand each of these counting formulas, because this will actually help and benefit you a lot in your exams. Because I personally do not follow, there is one professor, I don't exactly remember his name, but he said that mathematicians need to be lazy for them to find out shortcuts of things. Now this is not exactly a shortcut, but it's a shortcut approach, I would rather say. Not going into a very rigorous mathematics by just counting out tau, identifying tau specifically so that this happens. But nevertheless, what you can observe, the only thing which we required here is that what is the cycle type of sigma. We didn't even require how sigma looks. Are you getting my point? So this is very important from an exam point of view. You need to keep your mind open so that you are able to observe these things. Okay, fine. Let's move on to question 6. So let G be an abelian group of order 35. So G is an abelian group of order 35. What does that mean? So if G is an abelian group of order 35, that means that G is isomorphic to Z5 cross Z7, and hence it's isomorphic to Z35. So it's cyclic. solution. So it's cyclic. Now let M denote the number of elements of order 5 in G. So since it's cyclic, we know that, so I'm just writing it down. In a cyclic group, number of elements of order M is exactly equal to 5M, and we're done, right? So therefore M will come out to be phi of 5, which is 4. N will come out to be phi of 7, which is 6. So M plus N should be equal to 10, and you're done. That's your answer. See, so easy these problems are typically, right? But for to be able to solve these sort of problems quickly, you need to have a great conceptual depth. And the theory lectures, probably there are 8 theory lectures, so you need to go through each of these lectures very minutely, because there are a lot of informations. See, group actions are not specifically in your syllabus, but once you are able to observe these particular problems through group actions, see how easy it becomes. So you should allow yourself to learn new topics and advanced topics, so that, because the more advanced topics you learn, some problems become extremely easier. Okay, next question is that the number of surjective group homomorphisms from S4 to Z6. Okay, so fine. So solution, see, firstly, if phi is a group homomorphism from S4 to Z6, then phi of S4 should be equal to Z6. So therefore S4 divided by the kernel of phi should be isomorphic to Z6. So therefore you need to identify kernels so that it's identified exactly by Z6. Now what are the normal subgroups of S4? So normal subgroups of S4 are, so you have the trivial group, you have the Klein 4 group V4, or often I write it as K4 as well, you have A4, and you have S4. Now S4 mod S4 has cardinality, it has cardinality 1. S4 by A4 is isomorphic to Z2, which is obviously not isomorphic to Z6. S4 by V4, so V4 has cardinality 4, so it's actually has cardinality 6. Okay, so this is typically the only possibility you have. But now you can take this as a very interesting exercise, or probably we have also discussed this in some previous lecture, that S4 by V4 is actually isomorphic to S3, which is not isomorphic to Z3 because this is non-abelian. Okay, so these are the only possibilities you get, right? So there should be zero surjective homomorphisms. Okay, let us move on to question 8. For a positive integer n, okay, so again a question from UN, which of the following statements is true? U5 is isomorphic to U8. Now here observe that U5 is cyclic, while so let me just write it down here itself. So this is cyclic and this is not cyclic. Okay, see, 10 is equal to 2 times 5 to the power 1, so it's cyclic. 12 is not cyclic. U12 is not cyclic. U8 is not cyclic, while this is cyclic. So the only possibility you are having is basically this. So this should be the correct answer. But nevertheless, you can actually find out the value of it. So what is the cardinality of U8? It is phi of 8. And what is phi of 8? So it is 8 times 1 upon 2, which is 4. And so a group of order 4, if it's not cyclic, then the only possibility is that it's isomorphic to Z2 cross Z2, which is exactly V4. And the same happens here as well. So phi of 12 is 12 into 1 upon 2 into 2 upon 3. So this is 2 and this is 4. And since it's not cyclic and a group of order 4, so it's also isomorphic to Z2 cross Z2. So they has to be isomorphic. See how easy these particular things have become, right? So I'm just writing it down. So un, it's basically zn cross set of units of zn multiplicatively, and cardinality of un is basically phi of n. And the reason being that an element in Zn is a unit, is a multiplicative unit if and only if it is co-prime to n, and those form the collection un. Okay, let's move on to question 9. Which of the following is true for the symmetric group S13? So they want elements of certain orders, and so just you need to just think of uh, products which can LCMs of elements, right? Cycle decomposition, so LCMs of element. How do you calculate orders, right? So if you have a cycle decomposition, say I1, I2, and say In, it's a cycle decomposition, then the order of such an element with which admits the cycle decomposition is just LCM of I1 till In. So that is the only thing which you need to keep in mind. Okay, see 27 is 3 cubed, so you probably won't get a partition which has LCM 27. See, here you have 7 plus 6 equal to 13, and LCM of 7 and 6 is actually 42. So this does, and we're done. Right? See how easy this is. And by the same condition, you can just cancel out each of these three. Right? Because you can take the cycle decomposition 6, 7. What element would this correspond to? So you take cycles 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12, and 13. That's it. This will have ordered 42. Okay, so finally the last question from IIT JAM 2024, which says the following. So let G be a finite group containing a non-identity element which is conjugate to its inverse. Okay, then which of the following is true? Okay, that is a good question. So what is being asked? So solution. So G is so there is an element X in G such that there exists G in G with X being G X inverse G inverse. So this is what you have, right? This is exactly what you have. Fine. Okay. So the order of G is necessarily even. Okay, first thing first, so this is a very important thing, that the order of an element and order of any conjugate to it is the same. Okay, and this is a very easy thing to prove. So now this implies that order of X is actually equal to order of X inverse, right? Does this actually help us? It actually does, right? Because that would mean just let me think of this. Okay, so I at least have this in hand, right? Now see, if X is equal to X inverse, then this is true, then this is true trivially because it's conjugate via the identity element, and then you have order of X to be equal to 2, right? Because this would mean X squared equal to 1. So since order of X divides the order of G, this should mean that order of G is even. Okay, so the order of G is not necessarily even. Fine, the G is necessarily cyclic. Does it need to be cyclic? I don't think so. I don't think so. It needs to be cyclic. So we need to analyze the case that, so suppose X is not equal to its inverse. We need to analyze this particular case, right? How should we proceed? Okay. Let me just think of it once. Okay. So let me take some space. So I'm removing this part. Okay, so I hope you just understood the first case. So I need to analyze the case when x is so solution. Suppose x is not equal to x inverse. I need to analyze this particular case. Okay, suppose, so the obvious thing which I would like to just induce here is that suppose the order of G is odd. What does happen then? So okay, so first thing, so this implies that every element in G has odd order, right? Has odd order. Now let G to the power 2k plus 1 is equal to identity. So this is the G we chose. Okay, so what do we have? So we have Gx G inverse is equal to x inverse. So if I conjugate G one more time, what do I get? So I get G of Gx G inverse is equal to Gx inverse G inverse, right? So this is nothing but Gx G inverse whole inverse, which is x inverse. So this implies G squared x G to the power minus 2 is equal to x inverse. Okay, did I do it correctly? No, sorry, it's x inverse whole inverse, so it's x, right? What if I do it once more? So then G cubed x G to the power minus 3 should be Gx G inverse, which is exactly x inverse. Okay, so fine. Okay, so now by induction you will be able to prove it. At least I can see a pattern, so I'm not getting into the induction. So by induction, G to the power 2k x G to the power minus 2k, this will become x, and G to the power 2k plus 1 x G to the power minus 2k plus 1, this will come out to be x inverse. So I'm just setting this to be G to the power 2l plus 1. So therefore for L, for k equal to L, G to the power 2l plus 1 x G to the power minus 2l plus 1, this should be equal to x inverse by what we got. But since G to the power 2l plus 1 is equal to identity, that means x is equal to x inverse. So that's a contradiction. Yeah, done. So that's a contradiction. Yeah, so therefore the only possible case is x is equal to x squared. In that case, the order of x will come out to be 2, and hence order of G is even. So therefore the order of G is necessarily even, and that should be the correct answer. Fine, so we got involved into a lot of very interesting problems in groups. In the next lecture we will be solving from questions from question 11 onwards, and after a bit of IIT JAM problems we'll get into CSIR NET and TIFR problems. Fine, so meet you guys in the next lecture.